I'm Justin Szaday, a PhD student at the Parallel Programming Lab. And today I'll be talking about some of the advances in the Charm++ languages. Just to give a quick overview of the talk, I'm going to do some comparisons between Charj, which is our general purpose programming language, to Charm++, and give some examples along the way, and talk about some of the embedded domain-specific languages that we've been working on within Charj, briefly discuss some of our future work, and then wrap up the talk. If time allows, I will provide some more substantial examples as well towards the end. So, like I mentioned, Charj is a general purpose parallel programming language. It's based on the Charm++ runtime system, and its primary goals are to lower the barrier of entry to the Charm++ ecosystem by improving developer productivity. It accomplishes this by supporting Charm++ concepts as first-class citizens. So this includes chars, proxies, char arrays, and all of the familiar concepts. And we use static analyses to facilitate and encourage parallel programming. So we want to try to verify things ahead of time if we can. And we also would like to bring some more modern features to Charm++. All of this is fine and well, though, but unless it generates performant code, it probably won't see adoption. So that's another high priority task. And we also would like to try and ensure some degree of performance portability along the way. So historically, HPC developers have been unwilling to adopt new languages entirely. So some other last minute concerns would be providing like mechanisms for wrapping existing code in Charj, like a foreign function interface, and making sure that our code is usable by other applications so that we can do piecewise migrations of applications to Charj. The most recent iteration of the syntax is somewhere between C and C++ and Scala. And this maintains some degree of familiarity while allowing us to bring in those modern language features like type inference and pattern matching. So this will be familiar to anyone who's sort of done Charm++ development, but I just would like to take some time to compare things. Classes are made into char types using the char keyword, and we have a main char keyword for main chars. And then you can also append various modifiers to that keyword, such as array1d for collections. And then we also have a proxy type that we use to denote proxies. And here's an example of what that looks like. We would have a main char named main, which has an entry definition, an entry method for its constructor. And within that constructor, it creates an array proxy, which is an array of 1D or a 1D array of chars called hello. And the key thing to note here is this proxy n semantics, which would kind of be like cknew in C++. So everyone knows that we access chars through proxies via entry methods. And in Charj, these are just char member functions tagged with the entry keyword, which may itself have various attributes such as local, threaded, async, and etc. I mentioned async and local particularly because only these types of entry methods may have return values. And in Charj, there are some niceties for handling these types of entry methods. So sync entry methods will block the caller until they complete, which means that they have to be run in their own user level thread so that they can be blocked. So only threaded entry methods are permitted to make calls to sync methods, and we enforce this using static analysis. Then we also have asynchronous entry methods, which return a future value that may be pulled upon until that value is available. This waiting operation would itself be like a call to a synchronous method, but polling is not worth noting. Or polling is not a synchronous call, sorry. So here's an example of what that might look like. If we had a char that had an asynchronous function and a sync function, and both returned an int value, when we called them within a threaded entry method, we would just say thread test proxy.syncfung, and then that would wait on the value, and it would just return an integer value. But if we call a asynchronous function through a proxy, it's automatically wrapped as a future, and then that future value can be waited upon using this hashtag symbol. One other thing to note is that Charj has traits kind of like Scala, and these can be used to share interfaces between chares. They can't be instantiated directly, but you can have proxies of trait types. And here's an example of what that looks like within Charj. We just have a responder trait, which is templated with some value t. And then this class here, my int responder, implements it with some specialization to just integer values. And then we also have to specify that it's an override within there. So one other nice sort of feature that I'll talk about within Charj is the support for custom reducers. You can just use the reducer keyword to tag a reducer, and you tag it with the type of value that's being reduced. So in this case, this is like an integer max function. It selects the bigger of two values. And the left-hand operation can be, the left-hand argument is sort of like an accumulator usually. And so then you would just, instead of having to do the registration yourself and keeping track of an ID for the reducer or perform any sort of message unpacking, the compiler handles all of that for you. So the typical Charm++ application compilation process is that you would provide like your C, C++ source files and a Charm interface file and any other headers and that kind of stuff. And all of that would be compiled to form the Charm++ application. But in Charj, we use simply write one.cp file, and that's compiled via the Charj compiler into all of the other familiar headers and wrapped into the application for you. We also have some support for various types of code analysis and transformation passes. And we have a rewritable intermediate representation that's shared between Charj and some of its embedded domain-specific languages. These passes are ordered according to dependencies, and I'll talk a little bit more about that later, but they can sort of be interleaved, and that's why there's that sort of symbol there. So why would we want to support embedded domain-specific languages? Well, a single programming model may not be suitable for representing the entire application. And we would like to give users the ability to choose the right tool for the right job. There may be some types of models that are incomplete and cannot represent all types of parallel computation, but can provide elegant representations or optimizations to certain classes of computations, such as Charisma, which I'll talk about in a moment. Furthermore, this sort of multi-model approach encourages modularization and thereby library use and code reuse. And embedding allows different models to exist side by side, trimming any redundancy that may have existed previously. And the execution of all of these different models can be interleaved simultaneously. So a familiar example would be stack-like operations. And within Charj, we have support for a when keyword that's internally implemented using futures. So pass goes through and does this simple transformation to every when method. Basically, it creates an entry method for that sets a future value, and then within the entry method that called that when, or within the entry method that contained the when block, it's tagged as a threaded entry method, and then that polls on the future value. And I mentioned this because Charisma, which is a language for orchestrating the global view of control for parallel programs, is internally translated to stack operations. So Charisma is a language. Previously, it was a standalone language that employs a macro data flow approach for parallel programming. We represent this data flow using a publish consume paradigm, which can capture a wide range of static data flows, but not any sorts of data-dependent data flows. So a simple example of that would be just every neighbor in every element within a 1D char array sending a value to its rightmost neighbor, and then the last element wrapping back to the first element. Within Charisma, it would look something like this. We would have a placeholder array, which is sort of like a fixed size indexable channel, but it doesn't really get created at any point, and I'll show what I mean by that in a moment. The actual orchestration code is this for loop here, which goes through all of the indices within the index space of a 1D char array. And then every element produces a value, sends it to its rightmost neighbor via the values placeholder. And then every element goes through and consumes a value from that placeholder. And there's an implicit barrier at the end of the for. So what does this get compiled to? Well, it just gets compiled to a when block. So each value, so now every element is producing a value and sending it to its rightmost neighbor. And then when that value is received, it's just consumed in line. A slightly more sophisticated example would be just Jacobi relaxation. And so here we have two placeholder arrays, one for the left elements and one for the right elements. And every char is going to produce two values. We'll return a tuple in this case, and then consume those values in a compute function and do a global reduction over the error. And this will continue to loop until the error goes below some threshold. So why would we want to make Charisma an embedded domain-specific language? Well, like I said, it was a standalone language before, and this meant that orchestrations were separate from everything else in a dedicated file, and char structures were in fact defined in multiple places because the char structure had to be within the orchestration file and within the charm interface file. So by making it a DSL, we avoid this redundancy. We're also able to reuse parts of the shared infrastructure, such as type checking, and all of the orchestration definitions and entry methods can be within the same place, as shown here. As orchestrations have become a special class of entry methods, the chars managing an orchestration are readily apparent, whereas before this was entirely invisible to the user and just simply internally managed. And by that I mean that, so now you can see that Jacobi 1D is the char that is, so I would say managing this orchestration because it's where the communication is taking place and where the computation or where the values are being routed. So the next embedded domain-specific language that I would like to talk about is called multiphase-shared arrays. And multiphase-shared arrays are arrays that have a shared global address space and can be synchronized between read, write, and accumulate only phases via a barrier operation. This stems from the observation that applications tend to access arrays in phases of reads or writes. So we do not allow interleaving of reads and writes, and this phased in execution model leads to like a simplified PGAS model. Updates and invalidations are only necessary at the time of the barrier, and remote values only need to be fetched during read phases. So this allows for various simplifications. Before, it was just a library within Charj written in C++, and this had some downsides because its syntax was a little bit verbose and complicated at times, and there was no support for custom analysis passes for correctness checking. For example, we don't want users to do a read operation when the array is in a write phase. So to overcome these limitations, we're working on an embedded domain-specific language where users can manually infer or can manually specify phase changes, or the compiler can infer them for them. The cornerstone of all of this is phase analysis, which is built on control flow information. So here's an example of what that would look like. So this entry method would be within a 1D char array. Every char within that array is going to enroll in the MSA, which tells the MSA how many chars to expect at the barrier. And then it's going to do a bunch of writes to that MSA, then do a bunch of reads to it, and eventually contribute a value somewhere. And if we take the CFG for that, the control flow graph, we'll see that there's one node within the each for loop where there's either a read or a write operation. So phase analysis starts by propagating this the phases between nodes. So the write is sent to all of the nodes that it can reach before the next operation, and the read is propagated to all of the nodes that it can reach. And then we insert two phase changes accordingly, one to be the initial change from the unknown status to write, and then later a change from the write phase to the read phase. And sometimes these phase changes may be inserted in like a redundant way or inside of loops. And we don't want to do a write sync when we're already in a write phase. So we have an analysis pass that goes through and eliminates those redundant phase changes. And if there is a phase change within a loop, we don't want to do it every iteration of the loop if it's the same phase. So like if every iteration of the loop has a write change, then we just want to move that to the beginning of the loop, which is what we can see here. So as for some of the future work, this talk really doesn't have anything to say about the performance yet, because we haven't done much evaluation there, and so that'll be a major priority going forward. And we have to also develop like a simplified intermediate representation, because the rewritable intermediate representation that we're using right now is actually Charj's AST itself, and this can be a little bit difficult to extend, and it's pretty hard to compile. So we would like to move towards something that targets LLVM or MLIR as we go forward, or maybe just like a simpler intermediate representation that still maintains, or that's still compiled to C++. We also don't have any interoperability in the current iteration. In fact, the code is generated in a way that's pretty unusable by existing applications, and there's no foreign function interface or anything like that. So suffice to say, the current iteration of Charj is still unreleased. We have some quirks to work out, but if you would like to test a pre-alpha version, feel free to reach out to me. We're also looking for other candidates for embedded domain-specific languages. So maybe a language that performs HPF-like array operations, something specialized for tree operations. We're still trying to think about what would be useful on that front. So to conclude, Charj is a general-purpose parallel programming language based on the Charm++ runtime system. It supports multi-model development of parallel applications by embedded domain-specific languages. We have a couple of examples, SDAG, Charisma, and MSA, as far as languages that are currently embedded within Charj. And before I hand things over for questions, I think I would just like to show a couple other example programs. Namely, this is just a simple Fibonacci computation here where it spawns two chars underneath it, and or where it recurs into two chars every time. And so here's sort of where some of that C++ familiarity comes in. We would take in some command line arguments and then convert the strings to integers and etc. and just print the results out, create a new Fibonacci, which has this trait responder, and then it'll recur and create two more underneath it and continue going. And there are just a couple other example programs that anyone who's interested, I could share with them as well. So with that, I will go ahead and conclude my talk.
Thank you, Justin. Looks like we have one question in the chat from Nils asking if you're planning on writing syntax highlighting plugins for editors.
Yes, that would be desirable. Syntax highlighting for like VS Code would be probably one of my first priorities, but other ones could be considered as well.
Great. Are there any other questions in the chat? If nothing posted in the Google Doc or anything last minute you'd like to discuss with Justin? Well, are there any other questions or anything last minute that someone would like to discuss with Justin right now?